Okay, welcome to section 6.4. Our objectives are I can solve special systems of linear equations in two variables and classify systems of linear equations and determine the number of solutions, how many answers those two share. Just a reminder, when you have a graph like this, if you have a line going this way and maybe a line going this way, where they cross is your solution. So they could potentially have more than one solution. They could potentially have no solution, or they could potentially have all the solutions if they are indeed the same line. So we'll talk more about that in a minute. So first of all, you saw that when two lines intersect, like I just showed you, this is called consistent. Okay, if it has one solution, at least one solution, it would be consistent. So if you have an answer, it would be consistent. Now, if it does not have a solution, meaning you have your graph, you have a line going this way, and you have a line that's parallel, so it never crosses, it's called inconsistent. Okay, so emphasis on its parallel. It's an inconsistent system. It has no solution, no answer. So we're going to show that this one has no solution. So you got a line here and another line. So this is one way that you can do it. You can compare the graphs, or the equations, I mean, by writing in y equals mx plus b form, slope-intercept form. And when you look at this, you see that they are parallel because of the slope. And since they are parallel, they're never going to touch, they're never going to cross, and so your answer would be no solution. Another way you could show this is by actually just solving for x and y, figuring out what the solution would be. So what they did was they said y equals this, so they plugged this in for y, used the substitution method. And then they just solved for x, and you notice that my x's cancel out right here, and they get -4 equals 3. -4 does not equal 3 last time I checked, so this would be a no solution. So whatever method you use, it will work that way. I'm going to be using this method to show you guys. You can use whichever one you want, whatever one you're comfortable with. Just make sure you familiarize yourself with whichever one you use. So we're going to show that this one has no solution, and you can already see when you graph them, oh, this is still the same one, just kidding. When you graph them, you can see that they're parallel, but this one, we already know it's no solution, but we're going to show. So I have y equals this stuff, so I'm going to take this stuff, and I'm going to plug it in for y. I'm going to use the substitution method. So 2x plus, okay, well this is y, so I'm going to plug that in, equals 1. See, I just plugged it in for that. Okay, now I'm going to clean it up, and I get 2x minus 2x, that goes away, and then I get 5 equals 1. Well, that's not true. So this shows that we have no solution. That would be an adequate way of showing no solution. Okay, if two linear equations in a system have the same graph, meaning if you have your grid here and you draw a line and you have an equation for the same line, it's a line that's lying right on top of the other line. This is called coinciding. Coincide. These lines coincide. They have all the solutions. They share all the solutions because they cross everywhere. And this goes on forever. They coexist in the same space. They are the same line. So this is all solutions, or you can remember I said it was all real numbers, that fancy R. Or you can say infinitely solutions, infinite solutions. Or you can say all solutions. Or you can say all real numbers. Any of those would be acceptable. These are just 4 different ways you could write it if you want. So for this one, show that it has infinitely many solutions. So show that these lines are, in fact, the same line. So this first method, they rewrote it into y equals mx plus c form, and you see they have the same slope, but they also have the same y-intercept. These coincide. These are the same line. Okay, oh, it says right there too. But there's infinitely many solutions, infinite solutions. Whatever you feel like writing. That fancy R, infinite solutions. Okay, and this is the other method. So before, when we solved it, we got something that wasn't true. When I solve this, I get 0 equals 0. which is true. So if you get an answer that's true, that means that it's infinite many solutions. These are the same line. All the things I could possibly plug in for x or y will get me a true statement. And just recognize that 0 equals 0 is a true statement. It does not mean that it has 0 solutions or no solution. You're just checking to see if what you wrote is true or not. So if your x goes away, if your y goes away, and you just have numbers, so let's say you get 2 equals 3, that would be false. That would be no solution. If you get 3 equals 3, that's true. That would be infinite solutions. Same thing if you get -2 equals -3, that would also be false. So you're just checking to see if it's true or false, whatever you get to. Okay, let's show that this one has infinite many solutions. I see that y equals this stuff, so I'm going to take this, I'm going to plug it in for y right here. So x minus, okay, starting my y, x minus 3, and then minus 3, that 3. Okay, now this is a slightly tricky part. The reason why I put this in parentheses is because I have to distribute this -1 in. Okay, now x minus x is 0, 3 minus 3 is 0, so I get 0 equals 0. Is 0 actually equal to 0? Yes. So this is infinite many solutions. Infinite solutions. If you have trouble writing the infinity sign, if that's the method you're choosing to write, it's just a sideways 8. Okay, some more terms. So within the consistent systems, and you just remember that consistent means there's at least one solution, they can either be independent or dependent. So independent is what we've been doing before. It has one solution. One solution. Dependent system has infinite solutions. And the dependent system has to do with the coinciding lines. Coincide. So the lines that are exactly the same would be dependent. So if I have y equals 2x plus 3, and another line that's y equals 2x plus 3, those would be dependent. My independent example would be y equals 2x plus 4, y equals, let's not do that, let's do 3x minus 2. Those have one solution. And here's a breakdown of all of that. If that's confusing for you, you can look in your book as well. So you have your consistent options, which has at least one crossing point. And within that, you have the independent, which is one crossing point, or the coinciding lines, the same line, that has all the solutions, infinite solutions. And that would be dependent. Okay, and then you have your inconsistent, which would just be two parallel lines. They have the same slope. Okay, and now don't get confused with the same slope, because technically these both have the same slope, but this one has different y-intercepts. So if you have y equals 2x plus 3 and y equals 2x minus 4, see, same slope, different y-intercept. If you were to solve it like I've been doing, your answer would get something like -4 equals 2, which is not true. If you had a consistent and dependent solution, you'd get a true answer like 2 equals 2. That'd be true. And then if you had a consistent independent thing, you'd actually get a point. So you'd get x equals 2, y equals 4, or whatever. You'd actually get a coordinate point. So let's do a couple more. So we're going to classify the system and give the number of solutions. So I know you probably already saw the answer there, but let's solve it, see what happens. So let's see here. I'm going to take this one. And I like to use the substitution method. I just like it better. I'm going to get x alone because I see that x is already kind of alone. I'm going to subtract that 3 over. And I get x equals 3y minus 3. And I'm going to take this and I'm going to plug it into x on the second one. See, I just plugged it in for the letter x. Brought to you by the letter x. Now I'm going to distribute that in. And I have a negative 1y plus y on this side, so those actually cancel, and I get 1 equals 1, which means there's infinite solutions, because that is a true statement. So first of all, I have an answer, right? I have at least one solution. So this would be consistent. And since I'm getting infinite solutions, we're going to have dependent. And you can use that chart if you need to. It says it right here as well. You don't need to write a long sentence. You can just write consistent, dependent. Make sure you show all this work to show how you got there. Okay, let's do another one. I'll try not to show the answer this time. There we go. This one, let's see here. Let's try to get y alone right here. So I'm going to subtract this 4. I'm going to use my substitution method again. Okay, I'm going to take this and plug it into the y in the first one. Oops. And drop those parentheses. I don't need them. And, ooh, look, that cancels. So I get negative 4 equals 5, which is not true. So this is inconsistent. Just inconsistent. They're parallel. No solutions. Oh, sorry, give the number of solutions. No solutions. No solution. Okay, here's another one. Zoom that puppy in. And, ooh, I have y equals, so I'm just going to take this and plug it in for y there. Okay, and solve, so I'm going to distribute that. And 4 minus 3 is 1. Move the x over. And go over here. 1 equals negative 3x. Divide by negative 3. And I get negative 1/3 equals x. Okay, so that's point number 1. Plug it back in. I'm going to plug it into this second one. Plugging in for x. We're going to add 3, and that is 2 2/3. Whoa, that's the 3's. Okay, and it looks like I'm getting a solution, which means that these cross somewhere. So this would be consistent because I got an actual answer. Okay, I have one solution. It's that. And this would be independent because I only have the one solution. Okay, here's another one. Okay, I have x equals this stuff, so I'm going to plug right in. And distribute. And solve. So it looks like this cancels this out. So negative 2 plus 2 is 0. I get negative 4 equals negative 4. Ooh, that's a true statement. That means that I have infinite solutions. I have at least one solution, so it's consistent. And since it's all the solutions, it's infinite, it's going to be dependent. You can look at your chart if you need to, maybe write your chart on a note card. There you go. Okay, here's another example. And this time they both equal y, so I can just plug in for y right there if I want. distribute. And solve. So let's subtract that 3. And add that 2x. And I get x equals -1. And I can plug it back in. Let's plug it back into the first one just for funsies. And just solve. And so it looks like we get y equals 4. So this has how many solutions? 1 solution. That one. It's consistent. And it's independent. Okay, another example. Y equals this, so I'm going to plug in for y. And then I'm going to clean this up. We got 2x minus, and then the 3's kind of cancel each other out if you're comfortable with that method, or you can just multiply them. And we get 2x minus 2x is 0. 0 equals 6. Oh, that's not true. So this is inconsistent. There's no solution. Okay, so Jared and David in this problem both started a savings account in January. Good for them. If the pattern of the savings in the table continues, when will the amount of Jared's account equal the amount in David's account? So first of all, we need to figure out what's going on. So it looks like Jared started with $25. So we're starting with $25. And then we're adding a certain amount each month. Looks like we're adding $5 each month. So $5 per month. And see, I came up with that equation right there. And then we're going to equal our y. Now take a moment and see if you can come up with an equation for David's. So what did David start with? David started with 40. And then what did we add each time? We added $5 per month. And remember, per means times, and month is my variable. And this is going to give me my y, which is my total amount of money over that amount of time. Now thinking logically of this, when will they equal the same amount? Well, David started further than Jared, and they're both consistently adding the same amount each time. So if I were to graph these would be 2 parallel lines. But let's solve this algebraically. So here's what they wrote. And if you were to actually solve them, let's set them equal to each other there. So when will they equal each other's amount? And you see I take away the 5x from both sides and suddenly I get 25 equals 40. That's a no-go. 25 does not equal 40, last time I checked. So there is no way that these two would have the same amount over the same amount of time, which kind of is maybe an eye-opener to you. The sooner you put money into your bank account, the more money you'll have over time. So David is setting off to a good start here. Now, if Jared wanted to catch up to David, he might want to up how much money he's putting in each month. Maybe increase it to like $10 per month. But there you go, real life application for you.